Hello, and welcome to Class 3 of Particle Fundamentals and Fuzzy Logic. In this class, we're going to get into rotations. And I found overall in all of the TDs I've worked with that rotations is one of the most misunderstood and daunting areas, and it took me many years to really get a grasp of things myself. And that's why I think it's really important, because a command of rotations, it might be great for the example we're doing, which is rotating a shark gradually to face its target, but it comes in handy in just so many ways. It really frees up the TD from working basically in rigging at object level, and it frees up the TD instead to really command transforms at a geometric level. Positions and scales are quite a bit more straightforward most of the time. It's really rotations that gets people. So here in this example, we're going to add to our system. We've already made the system in the previous classes swim toward the target. And now we want to add a really crucial piece, which makes the shark progressively face the target instead of just an absolute switch. See, so here I've got a little digital asset I made to provide various previews of targets. So in this case, it's a circle, and it's just emitting a single particle. And it's changing the position of the particle every 6 seconds. And this is the circle just for a reference of scale. Okay, we're still previewing with a rigid shark for now. And I'm viewing the target at geometry level. And let's just take a look at what's going on in the finished system before we try to apply that to our work in progress system. Okay, so most of the action is just happening in here for now. In the next class, we're going to add on some more axes, such as the tilt direction and the up and down swimming directions. But for right now, it's really just going to rotate on this plane. And what's going on in here? So we can ignore a lot of these inputs because we're going to build those up later. But the main input to pay attention to is incoming of the shark direction, incoming of our target vector, the thing that's always absolutely facing the target. So here's our target vector. Let's see what's going on here. Okay. So the yellow one would be the absolute direction, and the pink one is the current direction of the shark. The green one is the up vector. The up vector is the direction of the upwards shark, because one vector just isn't enough to describe that. This shark could be rotated on any number of things. So it's really important before we undertake this that we have this nice little green guy up here telling us what direction is up, and that allows us to rotate on this guy like a spinning top. So in comes the shark direction, in comes the target vector, in comes the up vector. And then we're going to perform this turn based on adaptive timing, and we're going to further adapt to make it give it a little bit of lag in its decision making. And then finally, we're just simply going to apply this to the rotation. We're not going to do the banking yet, although that is a really nice thing to do in this case in particular. And so we'll do that in successive classes. Let's get started. So just hitting play here, we've got our system working from the previous class. And notice we don't even have a shark up, which we need to create. Okay, so the first thing I want to do to really test this system out is let's stop the shark's movement temporarily. So here under the seeking behavior, we definitely want to keep the target vector. We really want this guy. But with the seeking behavior, let's just temporarily not add to the velocity. See if that works. Okay. And notice the absolute rotation. Right now, the shark direction is simply being hard-coded, and this really isn't about rotations. Right now, this is simply a subtraction of these two vectors, which is hard-coding the direction. So let's do a little more than that. So let's start building our rotation system now. Okay, So let's keep this in a different node because it's a fairly different operation than the position. And it's really good to be able to turn things on and off. So I would recommend selecting broad sweeping categories for your particle logic nodes. There we go. And diving in. So as I said before, we need to bring in the shark direction. And right now, this is simply being set from the gather of the target vector, and then the seeking behavior needs a direction to go to. So that's where I'm setting this parameter right here. But really, we want to take the shark direction out of our system here. Okay, so I'm just going to Control X that. Now it doesn't have any direction. Okay. Yeah, we're just using it right here. So the idea is we're going to form a feedback loop. The shark direction goes out, and on the very next frame it comes in again. Without a feedback loop, we wouldn't really be able to change the shark direction. We also need an up vector. So temporarily, we're going to also dynamically set the up vector, but I'm just going to put a shark up in our target vector system here. Vector, export always. Let's have it default to upwards. Okay, so now we've got our default vector here. Okay, so in comes the shark direction. We also want a shark up. And then finally, we want our target vector. Okay, let's have the shark up default, shark direction default. So without any further ado, let's get this shark direction feeding back and rotating. So it's very similar to the position and velocity exercise we did in the introductory concepts. The only difference is we're going to be feeding back some rotation. So in comes the shark direction, out goes the shark direction. We can even call this export and import to keep things straightforward. Seems like a simple thing, but it's a lifesaver in a really complicated setup. Okay, so with this node, I'm going to use this to set parameter attributes. That's really important in particles. It means that it's not going to be setting from this one, it's going to be setting from this one. I'm going to export when input is connected, and there's no reason to have these guys on the interface. Okay, so in doing this, we've created a feedback loop. Shark direction goes out, shark direction goes in. All right. So there we have it. So now let's rotate about the up vector. So how do we do that? So a vector, it can be viewed as a line, and that's really the most common perception of it. However, it might be more useful in this instance to view this vector as a point instead of a line. This is also representing a point in space. So the tip of this line right here, if we get our shark direction, and we would instead view this as a point trail, I believe. So this is also a good way to think about it. And the reason I'm saying that is because we want to treat this like just any old piece of geometry, any old point, and provide a transform operation to it. If we view it as a rotation or a vector, we might be tempted to do lots of different like rotation operations to it, but really, and plug it into things like rotation. But really, we should view this as any old piece of geometry, and it still, the only difference between a vector and a point in space is that this point in space might be dependent on the world, whereas this vector is obviously represented coming from wherever our point that's holding these attributes is in space, but still it's just a position relative to the point. All right, so with all that, I'm going to make transform. Okay, so in comes the shark direction. I'm not going to plug this shark direction into the rotation field because really this is a point in space that I want to manipulate. So this is actually going into the translate, and out of this I've created a rotation matrix. Now that it's a rotation matrix, we can rotate the rotation matrix. All right, and this rotate works a little differently. It's a much more natural, organic way than we might be used to in the transform SOP. It's largely for animation. Human terms, this is more the way the computer would work, where it's taking a vector and it's spinning something about that vector. So this green one is going to be our vector that we're going to spin along. So that's where the axis comes in. Shark up is our axis. It's a good idea to normalize all these things before they go in. Okay, and then finally here's the angle. So this angle works in radians, and just because radians are a fairly difficult thing, at least in my mind, to animate with, I'm just going to make a parameter. I'm going to call that rotate degrees. And then I'm going to convert this from degrees to radians to feed this with the right amount. Okay, so in theory, this rotation matrix this transform matrix that's coming out of here, these 16 numbers, represents this point in space rotated about that. So we need to get at that information. So that's where we're going to extract transform. And that takes in a matrix, and it gives us these components. Now, we're once again not going to take out the rotation because this is a position. So we're going to take out the translate and put that into the shark direction output. So now we've created the feedback loop. Shark direction comes in, turn it into a matrix, rotate the matrix, convert it back to a vector, and then shark direction goes out. And then on the very next frame, it's going to keep doing this. And we're going to be rotating it by this amount of degrees each time. So let's try 3 degrees. And there we go. -3 degrees, maybe -6. Okay, so it's a progressive rotation because of the feedback loop. If it just happened once, then it would just rotate 6 degrees and that would be it. I'm going to put this back to 3. Okay, so now let's have a dynamic input. Instead of simply rotating 3 degrees in every frame, let's do something more sensible with it, like make it orient for this target. Now, for that, we have to get the difference, if you will, or at least the direction between this yellow line and the shark direction, the purple line. Okay, so what is this direction? Should it go this way or should it go this way? How do you figure that out? So any two vectors, here's the yellow one, here's the purple one, and if you imagine the third line of this triangle here, this is like a invisible plane that we could walk on. And any two vectors, whether it's this vector, whether it's this vector, whether it's this vector, any two vectors have a surface, and from that surface we can gather a third vector. So that third vector is the cross product. Okay, and cross product is super easy to do in VOPs because it's just a node. Okay, so what I want to do is I want to get the cross product between the purple one and the yellow one. And before I do that, we want to normalize the yellow one, because otherwise that could distort the result of our cross product. Okay, so here's the target vector, and here is the normalized shark direction. And we should, from this, we should be gathering that third very important vector. So here, let's just perform a test to see what this cross product looks like. We'll call this test A. Vector. Okay. And we can see that this vector is facing downward. Okay, and then as we rotate it, see how the vector is changing its direction. As the target changes, it changes its direction as well. Okay, normalizing this vector, we're going to get a very decisive up or down. Now, how do you know which side is going to be up and which side is going to be down? So whatever the first vector is relative to the second vector. Okay, so here we've got the target going in here, and we've got the purple one going in here. So looking in the direction of this vector going to this, this would be to the right. So that's called the right-hand rule. As that crosses over, looking to this direction, it's going to be, once again, going to the right. It's not looking in this direction. Okay, so we can tell if it should go up or down based on this angle. And why do we need something going up and down? Well, if you notice, it's either facing directly or facing the exact opposite direction of what it's spinning on, which is our up vector. So from that, we can get a very related operation, which is the dot product. Without getting too heavy into the math and more of a practical use of the dot product, if two vectors, the green one and the black one, are facing the opposite direction, and shark up. So if they're facing the opposite direction, it's going to be -1. Plugging this into the color, we'll see that they're opposite and -1. If it's going in the same direction, it's going to be +1. Exactly perpendicular, that would be 0, and the progression would follow suit. You can see that progression changing as I plug in a non-normalized value. Okay, and that's of a lot of value to us because we're going to use this to determine if it should be rotating to the left or rotating to the right. So here's our dot product, and then let's do a two-way switch. And we're going to say compare if this dot product is greater than or equal to 0, then we want to rotate our rotate degrees in a positive direction. Okay, so here's our rotate degrees coming in, and presumably that's in a positive direction, and then it's going to rotate that way. And if it's not, if it's less than, then we want to rotate in the opposite direction. So what we're after it finding the best way to rotate, the shortest way to rotate to get to its target. All right, so here's our condition. It's switching between the value and the negative value. Let's plug this in and see what happens. Now our rotation is 3 degrees, but in the direction it should be based on where the target is. So let's see if it rotates this way. And it's rotating the opposite way. Okay, so I messed that up half the time. So now I'm just going to switch these two things. There we go. And here we can see it rotated to get to that. And then once the target changes, it's going to always find the shortest path in order to rotate. Okay. Let's stop viewing the test vector for now. And right now it's forced to rotate 3 degrees one way or the other. So that's where the jitter is coming from. But we've successfully given it a very key component to adapt to an environment in its rotation. Okay. So now let's make it a little more pleasing to the eye and a little more realistic. Now's where the fun starts, because we're going to integrate a curve and make it rotate different speeds based on how far away these two vectors are. So if we have a big difference in these two vectors, we want to rotate pretty quick. And if we have a really small difference between these vectors, we don't really need it to be exactly that rotation and that jarring motion. So how do we figure that out? So what we want to do is we want to figure out the angle between the, once again, the shark direction and where it should go, the target direction. Okay, so in comes our normalized shark direction. And we want to do, once again, the dot product. And then in comes our normalized target direction into our dot product. Okay, now to figure out, now this is in the 1 to -1 range. We actually want to fit this probably 2 degrees as well, because we want it to be a little more representative to work with. So for this, to turn this dot product into degrees, I'm going to do the arc cosine. So in comes the dot product, and I'm going to do the arc cosine. And then once our radians 2 degrees, which is the opposite of the deg to rad. Okay, so that should be the degrees, and let's test this out in the color. Okay, so that looks like it's about 85 degrees. And as it gets closer, see, it's kind of going back and forth between 1 degrees until it gets close again. Okay. All right. So we've got this value. I'm just going to collapse this. Makes it a little easier to work with. Okay, so based on, now this is our another environmental factor. The first environmental factor is our direction. The second environmental, so that's, we're getting our sign. Basically, if it should turn positive or negative. In this, we're getting, you know, how much should it turn. All right, so now we can fit. We want to fit from degrees. So what's the minimum degrees? Well, that's going to probably be 0. We're looking straight at it, to the maximum degrees. So the maximum, we don't really know what we want for us. So for that, we can make that an interface parameter. Maximum degrees. All right, so on the interface, let's just say the maximum degrees that we want this thing to really contemplate is going to be about 100 degrees, a little more than a right angle. And we want to fit that to 0 to 1. Let's see how this responds in the color. Oh, as soon as it gets into rotations, it's really good to do a lot of testing, otherwise it can get confusing pretty quick. Okay, so here it's a fairly high, it's past 100, so it's red. And then as it gets closer, it's going to our no rotation value, and then needs to get there in a hurry when it's red. Okay, so now we can use this, perhaps make it even a little more organic with a curve. This would be the fuzzy part. It's going to move and adapt non-linearly. Maybe adapt rotation curve. All right, so if it's far away, if it's a 0, we don't really want it to adapt much. If it's 1, we want it to adapt 100% of the speed, and probably want a natural contrast curve. Okay, and now let's actually use this value for something more than the color. Okay, so here we'd really just need to multiply our rotation degrees by that. So rotation degrees comes in, multiply this by a scalar value. And you see it's really going to slow down because it's not too interested once it gets this far in. Okay. The other thing we might want to do is, once again, this is a fairly absolute value, and if we change the sample rate or the substeps, then this would change too. So we might want to multiply this by the time increment. And now it'll basically be 3 degrees of adaptation per second. Okay, so let's adjust this. It's going to be quite low. So let's say we want it to rotate pretty fast now, 120 degrees a second maybe. Still not fast enough. I mean, I think it should be able to rotate more than that. There it goes. All right. So this motion feels fairly robotic, even though we're using a curve. It's definitely smooth from the curve. It might be an appropriate rate, but it's just very exacting, and you can't really expect things in nature to work that way. Things in nature might turn and then they overturn and those kind of behaviors. So my kind of rule of thumb is, once we have a system that's working, then to make it work on the technical side first, and then once it's working, you can come up with ways to vary how it works to give it a more natural feel. And it's kind of like taking a step back and abstractifying, taking a factor that's right now being hard-coded and taking a step back and giving that some feedback properties. So the feedback properties that I'm going to focus on right now are going to be the basically how quickly it knows how far away the degrees are. Okay, because right now the degrees angle difference is being instantly computed no matter what we do between these two angles. And wouldn't it be nice if there's a bit of a lag, and then once it reaches target, there's a bit of overshoot? And we can do that by giving this a feedback loop. So for that, I'm just going to make a little subnetwork here. And let's make a new attribute. We need an attribute for a feedback loop so that it can be stored in memory for the next frame. So let's call this shark degrees adapt. Yeah, that's a good name. Okay, export when input is connected. I can make that invisible. And basically this is just going to keep track of this degrees. Use this node. Okay, so here's it'll be exporting the shark degrees adapt and importing the shark degrees adapt. Okay, so this will be the feedback loop. So in comes the degrees. This is the difference, the absolute difference. And we just want to adapt this value progressively. So for that, let's actually store this value. Just so we can compare the two. We have the shark degrees adapt, and now I just want to store the value for a diagnostic. Call this test dig, or absolute maybe, absolute degrees. Okay, so this is our absolute, this is the actual difference in degrees, and this is what we want it to think it is. All right. So now let's see how different it is between this and this. So the difference would be subtraction. We want to subtract the absolute degrees from the current degrees. Now, based on whatever this difference is, I want to add a set value, and that would be our adaptation rate. So here I'm going to get the sign, and this would be positive if it's positive, negative if it's negative. And then let's have this as our degrees adaptation rate. Okay, and I'm going to have that default to adapt by, let's say 10 degrees. And let's also multiply this by the time increment as well. Okay, so degrees adaptation rate, multiplying that by the time increment. Okay, so now we're going to either go forward or negative, just like we did with the rotation, except now we're just dealing with a simple float. And now finally, we're going to add whatever this value is. This is like our increment to this value. So here's the start of the feedback loop, and we're just going to add this value to that. Okay, so let's see if this adapts properly. Here's our absolute degrees, and we want to look at shark degrees adapt. Okay, so it's going in the wrong direction. So I'm just going to switch the subtraction direction. And now you can see it's trying really hard to catch up to however much it should actually be adapting. If we slowed this down, you can see a much slower progression. There we go. And the result, let's try out the result. So instead of just piping in and piping out our degrees, I'm going to pipe out the export shark degrees adapt. Okay, much slower, but it's going to wake up. Okay, now let's make that move a little faster here. So it takes a little while for it to get to full speed. All right, and we can find a balance. So notice here that we're still basically hard coding the sign that in the sign direction that it's going to turn. So it'd be nice if we had a little bit of follow through. So that can be done just with replacing this guy. So that's the difference of the degrees. And let's just actually use this for our end resulting degrees that we're going to turn. So let's see how that plays out just before we turn it into the radians and perform the turn. See, so now it's allowed to overshoot. Slow wake up and then overshoot. Okay. And let's see how this works if we turn back on our seeking behavior. Okay, so the final piece is it's not actually, it's doing its rotations and its velocities separately. So, and that's because we're getting everything we need from the target vector. So actually, let's replace the directionality component with the shark direction, because that's being set in the node below. There it goes. So now we're getting some really responsive and adaptive decision making. It's almost like it's catching up and always trying to align itself, and never this kind of hard-coded switching rotation behavior. Okay, so I hope you learned a bit more about the intricacies of rotations, and in the next class we'll work with the two other rotation axes that we haven't addressed. The tilt axis, meaning the shark up, and we can use that for other things down the road like banking as well. And then the upwards and downwards direction, which really isn't represented by an axis, but it's still present. So we'll take a look at that as well.